What if the order service is down? Using messaging, two services that are not even available at the same time can still talk to each other. You can even talk to a future service that does not yet exist, not deployed, not even developed. How's that even possible? Look closely. This is the order service in an e-commerce system that is using microservices architecture. The order service receives orders from different parts of the system, like a checkout service or different gateways. The question is, how will these two services communicate? If you ask this question, most developers might say through APIs, right? But then there are some problems. Suppose you receive millions of orders per day. What if the order service is down? Other services will try to call the order service, but the request will fail. What will they do? They might log the failure and move on. But this means you are going to miss orders. They might keep retrying for the next few minutes. But what if the order service is still not available? What if the order service stays down for 5 hours? You will lose thousands of customer orders with no way to recover them later. Now let's see the same scenario with messaging. Instead of using APIs to communicate between these services, we will use messages and then see how it solves the problem. With messaging in place, this service delivers its messages to a messaging system, which you can call a broker or a service bus. Once the message is delivered, the broker keeps it in a queue and returns an acknowledgement. On the other end, the order service subscribes to this queue and receives the messages as soon as they arrive. In our scenario, the order service is down right now. The broker keeps the messages safe in the queue, even while the service is down. And when the order service becomes available again, it picks the messages from the queue and does its job. Even if the order service stays down for 5 hours, other parts of the system continue sending messages successfully that remains persisted in the broker. As soon as the order service resumes, it picks all the pending messages at its own pace and processes them. With messaging, even after hours of downtime, no orders are lost. Orders may be delayed, but they are never missed. Now let's try to understand this through a simple analogy. Imagine an office where two employees work together. Employee 1 finishes her task and then tells Employee 2 what he needs to do next. For this communication to happen, both of them must be available at the same time. If Employee 2 is not available, Employee 1 becomes blocked and she keeps waiting. Now imagine a different way of working. Employee 1 simply places her notes on a table after finishing her part. Employee 2, whenever he becomes available, can pick up the work at his own convenience. This is what a queue does. It decouples the two entities that communicate with each other. We call this asynchronous communication. And that's exactly how a queue works in programming. At its simplest, you can even use a database table. One service keeps inserting messages in the table, and the other service reads them later at its own convenience, without depending on the first service. This is the basic idea of a messaging system. And then over time, this simple idea becomes more sophisticated to support advanced needs, introducing concepts like retries, persistence, dead letters, and more. But at its core, the whole idea is an abstraction layer built on a queue. By the way, it's also important to understand that inside messaging system, we have some other elements as well, mainly a topic or exchange and a queue. When a publisher sends a message, it is first stored in the topic. One or more queues subscribe to that topic, and those queues are then consumed by the consumer services. Now I'm going to show you the real power of messaging. But before that, let's see a quick 30 seconds code demo to actually see the scenario I just explained in action. This is the publisher service which sends messages, and this is the consumer service which subscribes to those messages. When the publisher sends a message, it goes to RabbitMQ, the broker. As soon as the message arrives there, the consumer service receives it. As you can see, it has been received. Now I will stop the consumer service while the publisher continues sending messages. All these messages are being safely stored by the messaging system, as you can see here. Now I will start the consumer service again. As soon as it becomes available, it begins receiving all pending messages, like this. Messaging is very powerful. It's the backbone of many modern distributed architectures. If you want to see how powerful it really is, then watch this carefully. Messaging gives you spatial and temporal decoupling. What does that mean? It makes you independent of space and time. See this. Suppose we have two types of orders, online orders and physical orders. Right now, both types are processed by the same order service. Later, we realize that they require very different logic, so it makes sense to move physical orders into a separate microservice. But here's the problem. Orders are coming from many places across the system. You will need to find all the places in every service that generates physical orders, update the code, and redeploy those services. But with messaging, we get a spatial decoupling. We simply extract the new microservice, we add a new queue for physical orders, and let the new service consume them. The old service now consumes only online orders. Notice something important. All traffic moves to the new service without changing any calling code. This happens because in messaging, the consumer decides that it wants to receive messages rather than publisher deciding who it is going to call. This is spatial decoupling, moving code to a completely different place without disturbing anything else. Let's look at another quick but very useful scenario. Suppose you have an SMS service that sends messages. Across the system, other services publishes the messages they want to send, and the SMS service subscribes and delivers them. Later, you decide to build a new SMS microservice using a different provider. You simply create the new service, stop consuming in the old one, and start consuming in the new one. See how seamlessly you move to a different version. This gives you replaceability. You can also shift gradually, starting with a small percentage of messages or moving only beta customers to begin with. If everything works well, you can then move completely. See how messaging opens the door to many powerful possibilities that help you build amazing systems. This is possible because messaging provides a strong layer of abstraction. See another interesting application of messaging. Suppose we have following notification channels: SMS, email, and WhatsApp. We can design it like this. Any service that wants to send a notification simply publishes a notification created event. All notification services subscribe to this event. Each one receives the message and sends notification through its own channel. Now suppose we want to add two more notification channels. We simply create new services and start consuming the same messages. The system is now able to send notifications on 5 different channels without modifying a single line of code in any other service. This improves modifiability. And similarly, if we decide to remove a notification channel, we simply stop that service. That's it. See how flexible this is. The caller services only publishes messages. They have no idea who exists on the other end. Now see temporal decoupling, which means being independent of time. Services no longer need to exist at the same time to communicate. Using messaging, two services that are not even available at the same time can still talk to each other. Try to understand this through a simple call versus message analogy. To call someone, both people must be available at the same time. But with a message, one person can leave it and the other can read it later and respond. Communication is no longer bound by time. The same idea has been used in software architecture. And of course, we call it messaging. We have already seen an example of temporal decoupling where a service that was down for 5 hours was still able to process its pending work. Now look at this. These two services are communicating through messaging. Suppose the system has been running in production for last 1 year. Now you build a new service and deploy it today, and yet it can receive the full history of messages throughout this time. Using messaging, you can even talk to a future service that does not yet exist, not deployed, not even developed. How is that even possible? Look closely. The messages you send today can be persisted in the broker when required, and later they can be consumed and processed by a future consumer. Think how powerful this is for analytics or when you introduce a more advanced version of business logic in the future. This also means that the future innovations can be applied not only to the new data, but also to the entire history. This is indeed very powerful. Event sourcing is a pattern especially useful in such scenarios. See one more interesting example. Suppose we need to run some midnight jobs. All the microservices in the system keep publishing the tasks they want to run as jobs. The messages are persisted with the broker. The service that executes those jobs remains turned off throughout the day. At midnight, it wakes up, starts consuming all the messages from the queue, run those jobs, and goes down again, saving cost. Again, see the flexibility. This would not be so simple without messaging. This abstraction allows the publisher and the consumer to remain decoupled and unaware of each other, which brings improved maintainability and flexibility. Another common use case of messaging in real applications is in IoT systems, where devices have low processing power and battery constraints. In such cases, it is not a good idea for the same service to both receive and process messages. If that service becomes slow or overloaded, IoT calls may fail or be delayed. So there should be a dedicated service specialized in receiving messages. For example, Kafka. IoT devices publishes their messages to Kafka, and consumer services then consume and process those messages at their own pace in their own style. Many real systems use this approach. Also note that consumers can choose to process messages in batches if required. Notice again, since the publisher and consumer are decoupled by this abstraction layer, they are free to work in different ways. Messages are published one by one, but consumed in batches. This is messaging, a simple yet powerful abstraction that can feel almost like magic. And that's why in modern architectures like microservices and other distributed systems, messaging is often considered a de facto.